Hello, everyone. Welcome back. This time to the last event of the semester at Robotics Today. I'm super happy to be today with Antonio Bicchi, professor of automatic control and robotics at the University of Pisa and senior scientist at the Italian Institute of Technology in Genoa. Thanks, Antonio, for being with us today. Antonio, he's a leader in the robotics community with research and service contributions that have shaped our community for more than 3 decades now. And Antonio's work spans many areas in robotics, right, including robotic manipulation, mechanical design, control systems, and haptics. And today he will talk about the important topic of the role and importance of impedance in generating physical interaction, both in humans and in robots. The list of Antonio's awards and recognitions and service, it's way too long to describe here. It's kind of daunting, but I just wanted to highlight a few things that I think that are impressive, especially in the service side. Just to sort of illustrate how much he has played a role in shaping our community, right? So Antonio, he has been chair at least once for RSS, ICRA, and ISRR, including other conferences, also including World Haptics, a conference that he helped launch in its first iteration. He has been the founding editor and chief of IEEE Robotics and Automation Letters. So he helped kickstart that new and very broad publication venue. And he has, of course, been involved in many European projects, large European projects within robotics. And for a lot of his service, he was recently the recipient of the IEEE George Sheridan's Leadership Award in Robotics and Automation. And the last thing that I wanted to highlight, which I think points out to some of his interesting relationship between Antonio and his students, is that at least 3 of his students have received the Best PhD Thesis Award in Europe, and 2 more have been finalists for that award, which sort of points to the degree of depth and competence of the research that he's able to transmit to his students. So thank you very much, Antonio, for all of that, for all of your contributions and service, and for being with us today.
Thank you so much, Alberto. You did embarrass me. Thank you. The talk today, it's a great pleasure to be here to share my views on some topics in robotics. Some of those that go back several years, but some are really recent, as of few hours ago. Let me share my screen with you. And so the topic that I want to cover today is variable impedance. Why is impedance important? I think robotics is an important part of artificial intelligence. Now, artificial intelligence is everywhere in the newspapers, in the politicians talking. Robotics is, a part, but it's a big part. And the difference between robotics and AI is that basically robotics is artificial intelligence fleshed out in the interaction with the environment. So whatever AI does to change the environment or touch the persons or do something physical, that is robotics. That means that interaction defines robotics. So it's planning and learning interaction then is a central topic for us. And impedance, the mechanical impedance by which you interact with the environment is a crucial aspect. That's why I think this is a topic that has been around for many years, but will always be with us. The presentation today, if I can start moving through it, yeah. Start looking at natural systems. Natural systems are not rigid, they are compliant, they are soft. And you see here some well-known examples of proboscis or humans. Uh, Compliance is used for many purposes, in some cases to absorb impacts or to have even better performance, like running or more explosive performance, adapting to the surfaces, or even in the elephant trunk case, do manipulation. It's everywhere in nature. If you go through the evolution tree, you find that all animals have compliance. It is a key enabler for adaptivity, therefore versatility, tolerance to errors, safety, robustness during interaction, energy efficiency, better performance. And of course, you have it through all the less evoluted animals, the invertebrates down to the vertebrates, and the human at the tip. There are different definitions of soft robots, but soft robots are machines that basically take inspiration from this ubiquitous feature of nature, of having compliance. In a recent definitions that Cosimo della Santina, Manuel Catalano, and myself tried to give of soft robotics, we considered that soft robotics can be of different times. Continuums of robotics take inspiration from animals that have no bones, basically invertebrates, and articulated soft robots instead take inspiration from vertebrates. In all cases, there are elements that define compliance and that define interaction. If you look at the human example, of course, we have bones, but we have muscles, and muscles are inherently compliant. So they are characterized by force deformation, force velocity, and force motor neural firing rate relationship. And there are descriptive models in the literature, but it's still an open topic in literature to exactly understand how the musculoskeletal system works in humans. The limbs have different stiffness because of their actuation through muscles. So if you combine two muscles in an agonistic-antagonistic configuration, in a push-pull configuration, then you'll find that the two characteristics of the two muscles combine so that you can have different stiffnesses at different levels of activation. Actually, humans change stiffness both voluntarily and involuntarily. When you lift a weight, you stiffen up, not because you want to, but because your system is made so that you increase your stiffness. But on the other hand, you can also change your stiffness without changing the position and without having any weight to lift. If you co-contract the muscles in the same direction, an antagonistic role. So this has been studied largely in the literature, and I'm very happy to have here one of the true pioneers of these studies, Neville Hogan, who as far as 1984 started looking into this problem. The fact that humans change stiffness, change impedance, use that changes for interacting with the environment in the proper way has been considered by many. So we have here also results by Cavato, Gomic and Cavato, and by Tiembourde, showing that in an experiment that you see on the top right, a person using a manipulandum to follow some trajectories and having perturbations at some point during these trajectories, perturbations that tend to create a diverging field from the trajectory that the person is trying to follow, learn how to change their stiffness ellipsoid so that to resist those perturbations in an optimal way. This is something that humans do. Humans use their stiffness and change their stiffness to do tasks. To do a task like this, the human had to be trained for quite some time to learn. It has been observed, on the other hand, that there is a strong correlation between the activation patterns of muscles that move a limb. And this affects how the stiffness of the limb is modulated. So it is not obvious for a person to shape the ellipsoid of the stiffness of the hand in directions that are voluntarily chosen. Rather, what it seems to happen more often is that we use posture to dominate the shape of the manipulability of the stiffness ellipsoid, and we use co-activation for controlling the volume. So when we contract muscles, we tend to contract all of them together. And it's difficult for us to learn to contract some muscles, but not some others in the arm. So the configuration-dependent stiffness, as we call it, changes with posture. And you see on the left a picture of a person that is pressing against a wall with the same force, but with very different impedance. Of course, the right configuration is much more stiff, as you can, and also to, therefore, to change the shape of the ellipse, the direction of the ellipsoid. While if you co-contract, you enlarge or shrink the ellipsoid, which makes every direction change in the same style. So this was work by Arasha Judani, a former student, now a colleague of mine, that also did these interesting experiments where we see how a human the human ellipsoid that is measured by perturbation by a robot arm changes in shape when co-contraction happens, but very little in direction, changing in volume, but not in shape. Now, this much given about humans, let's see what happens in robots. So variable impedance in robots has been used and proposed since long time. First, it has been proposed and implemented in software with variable impedance control. And then there have been several attempts to also implement it in hardware, in variable impedance actuators. Again, we can be inspired by nature and try to replicate that. And for instance, I share with you here the design of an actuator that has two smaller motors inside that you can see on the right here, and a connection between elastic elements between them that makes so that its force to the torque to deformation configuration is very similar to the human one. So by using these actuators, you can actually replicate the human muscle agonist-antagonist system in 1 degree of freedom. The actuator is actually rather compact, and it's even now a product of a spin-off company that you can use to simulate human impedance. This is work by Manuel Catalano, Giorgio Grioli, that you see here. Variable stiffness has been used for rehabilitation, for instance, with exoskeletons. I mentioned here some work from the University of Brussels for lower extremity exoskeletons. And in our own lab, we have done experiments using these cubes that I just showed before for exoskeletons that can change stiffness, but also for this knee. So in this case, you see that this exoskeleton is used to help the person lift. And the idea is that when you need more force at the beginning of the standing up operation, you better have a rather rigid motor because you need to transmit all that torque. While when you are standing, you don't want the motor to mess up with your freedom of moving. You do not need much support, and you want to have as low impedance as you want, as possible when you are in the upright position. Of course, there are other applications that we are working on. For instance, here is a prototype of an elbow for a prosthesis that has variable stiffness. And we are working on this. Of course, the effect of variable stiffness, as you can see in this example, is that you can absorb better impact, but of course with higher deformation. This is work by Simon Lemaire. The other possible approach to variable impedance is to use control. And there are very, by now, fundamental, basic results about how to implement this. Basically, if you have an estimate or a measure of the torques that you have at all joints, you can implement a system that has an apparent impedance at the teeth of the robot. And this is, of course, goes back to the famous work of Neville Hogan back in 1985, I think. This has been implemented in many robots in the labs, and recently even in industrial products. Of course, sorry. What happened? I went too fast. Yes. In reality, there are a few things that you can consider about impedance control. So in principle, by solving the equations of impedance control, I have here the simpler version of impedance control that goes under the name of stiffness control in the original proposition by Ken Salisbury. And you can see that by doing the rather simple manipulation of the Jacobian and the stiffness matrices, Kx is the desired stiffness matrix at the end effector, and J is the Jacobian of the manipulator, you can make so that the stiffness of a robot is any given desired stiffness, provided that you apply the right control. And this does not depend on the configuration where the robot is in principle, because you just take into account the configuration with the Jacobian. So from this equation, it would seem that it is possible to have an arbitrary stiffness ellipsoid in any configuration of the robot, as if it was not dependent on the configuration. This, of course, doesn't make much sense if you think that humans do change their configurations to obtain different stiffnesses, as I showed already with this picture. If you want to be compliant, you flex your arms. If you want to be stiff, you put them straight. Some work that we have done have elucidated the fact that in reality, what really counts is that we have limits and nonlinearities in the way we actuate torques. And even robots have limits in the torque they can apply. So if you consider those limits in torque, then it is not irrelevant which configuration you use to apply a certain stiffness ellipsoid. And actually, because you have basically a polytope that limits your torque application, then also your ellipsoid are bounded by a non-ellipsoidal contour, as shown in this picture on the right. So a robot has a larger capability of resisting forces in different directions depending on the configuration that you use. And this is something that generalized the impedance control to non-small deformations, because you can then absorb larger deformation and larger forces with these configurations. And of course, you can change impedance to do different tasks, as for instance, the very basic, very important pegging hold that we will come back together again. One point is now how to use variable impedance. Variable impedance and soft robots in general, they can be safer, they can be faster, they are more adaptable and more robust. but they are nonlinear. They very often are under-actuated. They come with lower control authority. They have lowered the relative degree in control theoretic terms. Therefore, they're more difficult to control. Here is a little classification of different robots. A rigid robot is basically made of geared motors and rigid links with an end effector at the end. Series elastic actuators are robots that are built with a flexible joint that has an actuator and a spring. It's called SEA, and rigid links. These have been historically the first prototype of soft robots that have been proposed in the literature from Gil Pratt from MIT in the late 80s again. Then DSA is a mechanism where you can change the stiffness by hardware and basically uses two motors whose combination can set both the equilibrium point and the stiffness. You can have also joints that are not actuated, but they have an elastic coupling. And therefore, you have some of these joints that are not directly actuated, but elastically coupled. So they can include some free elastic joints. Of course, you can have as many under-actuated joints as you want, with only few that are actuated, for instance, with ICA. And you can have robots where you even have robots that are free and are under-actuated, so only dynamically coupled, like, for instance, in the Acrobot or Pendubot examples from Mark Spong. And finally, you have continuum robots that you can see as an limit of a robot with many unactuated elastic joints and or flexible links. And it all depends on how you model these robots. So to control these soft robots, many different controllers have been proposed. And you have here a pictorial description of some of these methods. Methods that go in many different directions, from the most sophisticated nonlinear control, geometric nonlinear control, to neural nets, of course, to many other approaches, both data-driven and model-driven. To looking into the control properties of these all those robots that I discussed before, you can observe some features. First of all systems are controllable in their linearization, and all of those are input-out feedback linearizable with stable zero dynamics if there is at least some damping, inherent damping, except a specific class. You can do collocated control pretty easily, although you can have low performance. You can do non-collocated control. It's not impossible in theory, it's not trivial, but you can do. So there are tools for doing this. However, feedback control of soft robots is not obvious. And I want to share with you a very simple line of reasoning that I hope will make this problem interesting to you. So consider the simplest soft robot, which is a cart connected through a spring to a moving element. So basically, you move this robot by moving theta, the reference for this robot. And K is the stiffness. The system dynamics are obvious, are trivial. You have a disturbance here, and you control the position theta. So now assume that you do the simplest controller possible, which is a proportional control, meaning that you set the reference theta to K times the position Q, or the error, if you prefer. So what happens is that the system dynamics are modified by these KQ terms, and it happens that the effective spring stiffness is modified, that originally was Kp, is modified to K sorry, that was a small k, is now small k times 1 plus kp, and kp is the PID or proportional control gain. So the closed loop stiffness actually increases by a factor 1 plus kp. The stronger you make the controller, the stronger you give the gain to the controller, the stiffer the robot gets. And you can see that even a soft robot, here is a little arm that is built with those variable stiffness actuators that I mentioned before. And they are controlled in a very soft configuration here. When hits an object, because of the gain that keeps dragging the robot towards the goal, the robot actually becomes stiff, even though the control, the original setting of the joints was to be soft. So this clearly defeats the purpose. If you design a soft robot and then you control it so that it becomes again stiff, then why did you design it soft for the very beginning? Or you might say, oh, but that was just a naive controller. If I do a better controller, it turns out that that's not true. It turns out that, and I will skip some of these mathematics that are not very deep anyway. You can show that given any control law that has a feedback of the position and goes back to the torque, you can see that the variation of the stiffness that you impose on the robot, on the soft robot, can be described by this neat term, which is a difference between the derivatives of the torque generated with the controller and the torque that is generated in open loop. And that this knee, this change in stiffness, can be bounded by a given value delta only if the gain of the controller is lower itself than delta times the stiffness of the robot. This means that if you have a soft robot, you cannot change its softness too much unless if you want to keep the stiffness, the stiffness low, then you cannot have gain in the system, whatever controller you put. But the steady state gain has to be low. This means that basically you cannot do much in terms of using the gain. And of course, I think the easiest example of a controller that should not be used with soft robot is feedback linearization, which is a very strong, very, very powerful method. But see what it does. You start with these simple dynamics or any more complex dynamics. You feedback linearize, meaning you cancel all nonlinearities and you reduce it to a model where basically your input action equals the highest derivative in the system. And then if you do this, you have one input that goes to the fourth derivative in this soft actuator. You simply map your new inputs to the fourth derivative of some states. Now, question is, what is the physics? Where is the design of the soft actuator gone? This model is equal for all devices. These devices have been designed carefully and with some cost and effort to be soft. So if you do feedback linearization, every robot is the same. There are no softer or stiffer robots. So in feedback control, to sum up, performance is directly related to gain, that is stiffness. In a sense, if we have soft robots, if we want to have soft robots, we don't want to fight softness by control. And in some sense, one of the interesting things that soft robotics introduced in robotics and to our discipline is that you cannot rely on classical control, and you rather need minimally invasive control, if you allow me to use this term. How can we do that? So some ideas may come from how humans control our own bodies. If you see these videos that Roland Johansen proposed a few years ago, then you can see how a person that has been anesthetized in her fingertips initially, because she's lost tactile feedback, is initially in difficulty in the task of striking a match. But after a little trials, less than a minute, she can manage again all the motion control that is needed there. So if you look at the paper by Roland Johansen, you see that back in 1984, he already had very clear that sensory motor mechanism involved in the control depend in the motor control depend largely on predictive rather than servo control or feedback mechanisms. And that is a key. So anticipatory behavior or anticipatory control or feed-forward control is an important means that we learn in our early life or even later on to perform fast, powerfully, and accurate movements, even in the presence of perception delays. So how can we do this minimally invasive control exploiting anticipatory control for soft robots? There are two basic approaches. One is model-based and one is data-based, not surprisingly today. So first of all, how do we plan impedance? How can we optimize the impedance? Here is some work that my student Curie did with Sami Adadin, who was, of course, the leader of these very famous experiments, where we studied the importance of softness for safety of robots. That was August. The idea that you have a robot that has a rotor inertia and a compliance and a link inertia here, and a person that can be hit was formalized in an optimal control problem, can be formalized in an optimal control problem with a constraint that the impact anytime that happens anytime during the operation shouldn't shouldn't make too much damage to the person. So it's basically a brachistochrome problem. You want to move the arm from here to there in minimum time, but with safety limits. Along the trajectory, you don't want to be dangerous. Not to be dangerous, you have either to go slow or to have low inertia. And by basically acting on the variable stiffness of a robot, you can reduce the effective inertia at the link because the rotor inertia is multiplied by twice the gear reduction ratio, and therefore has a strong impact on the effective link inertia. So by changing both the stiffness and the torque at the joints, you can try to optimize for those values. And in some work that we did already many years ago, we showed that the optimal policy, by solving that optimization problem, the optimal policy is that you start a motion slowly and you go fast and you finish slowly, just as in most profiles of motion that you have in robotics. But if you look at the stiffness, that is more interesting. You want to be very stiff at the beginning when you're slow, and as soft as possible when you are fast, and then you go back to stiff when you slow down. And if you do this policy, then this method can beat basically both a rigid arm, a SEA arm, or any other combination. So the idea is basically fast and soft, stiff and slow for being safe and as fast as possible. But still, in the perspective of optimizing the choice of the impedance for a task, there are different tasks than just moving from A to B in a safe condition. There are tasks where you don't want to be safe, tasks such as hitting a nail. You want to minimize safety, actually. You want to maximize impact. So in this case, you ask yourself, what is the optimal impedance profile that I have to apply on the robot to maximize the impact on the nail? You want to have a max speed at free terminal time. It's a bounded torque. You can try to solve this problem with optimal control, and you find that the law tells you that you have to be stiff when you accelerate and soft when you decelerate. That's a very simple lessons that you learn from optimal control in this case. You want to be stiff when you speed up and soft when you slow down. And this was a result by Manolo Garabini and others, 2011. So here is an experimental example, still using those cubes that I mentioned before, in different stiffness configuration. You can see on the right the operation with the optimal policy is largely more effective than with the constant speed on the left. If you want to solve the other problem, which is maximize damping, so you have an impact and you want to damp it down, then not surprisingly, the policy is exactly the other way around. You want to be soft when you speed up and stiff when you slow down. This was work with Carlo Maria Gaspari, Lucio Pallottino, and Manolo Garabini. Another important application of this is when you want to interact with the environment. What stiffness should you use to interact with the environment? Assume that you want to press against the environment, and the environment has a curvature. In some cases, the curvature can generate instability. For instance, on the lower interaction scheme that you have, you see that a higher curvature can make the endpoint of the robot deviate from the normal position and go on either side of the bump. So there are issues with instability, resilience, minimum force to achieve the task, and positioning error. And there are some stiffness bounds that you can apply related to uncertainties, contact surface curvature, and interaction forces. And in this work that is more recent, 2019, by Riccardo Mengacci and Franco Angelini, there are quantifications of the limits that you can have. And also the experimental implementation of this shows that you have lateral instabilities when pushing, for instance, this button, if you don't set the impedance right. Okay, so far so good with model-based. You can do optimal control. In some cases, you can solve it symbolically. In some cases, you have to do it numerically. In most cases, you have to do it numerically. Sometimes you learn good lessons. But in many cases, the problem is just intractable. And in some cases, you don't have the model so good as to apply optimal control. So how about learning the anticipatory control that you have to apply? And the idea is, for instance, that you can repeat a given action with the robot and look at the outcome. At the beginning, you don't know very well how to move, how to control the robot. So you can control the robot along a trajectory. You'll see that is not working well. You look at the error between the execution and what you would have liked to have, and you change your control. So you do a next iteration, you try again and again and again. So basically, the control that you apply at the I+1 iteration of your trials is a function of the last control that you applied plus proportional to the error that you measured in the execution of this experiment. So this is called iterative learning control. It's been around for quite many years in robotics. And you see here is a forgetting factor. Basically, the new control is the old control with a forgetting factor, because you don't want to stick to the old one, plus a term that depends on the error that you measured on the last equation. You can also have a variation of this that was proposed by Mitsuo Kawato, where the R updating law also depends on the current error, the error that you have during the execution of U1+1. This is feedback. So basically, the calculation of ui plus 1 gives you a better approximation of the feed-forward action that you want to do, while the introduction of these terms give you the possibility of also using feedback during the execution. And this makes the system very general. You both have feed-forward and feedback. Now we want to use this approach to control the softness, and also to do that in a decentralized way so that you can control each joint basically independently. That you can do if you have diagonal dominance, and this implies again that the feedback action must be low. Let me skip some of the details here in the interest of time. And let's come to the, this is the paper by Cosimo della Santina, Matteo Bianchi, and others that settle this question, where you can find also the references. Here is the scheme that uses the informations that we have to converge to a controller that little by little improves on the former iterations and learn how to do the control while keeping the gain, the feedback gain, very low so that you don't perturb the softness of the robot. Basically, you keep the soft robot soft, but you execute the motion correctly. Here are some experiments where you can see that the stiffness variation was imposed from the exterior, while the robot could still perform the trajectory correctly, notwithstanding the stiffness. And here is the implementation. So on the left, you see the experiment that was failing before. On the right, now you see that these learning algorithms can perform correctly if there are no objects. And if it is set to be soft, it stays soft. So on the top right here, you see that the robot remains soft. Let me start this again. And indeed, it stops in front of the object, although the error is increasing because the gain is very limited. So this is interesting for many reasons. One is that we can control a soft robot without making it stiff through control, but also because there is some deeper theory that is recalled in the background. There was a fascinating paper by Roger Brockett, one of many of Roger Brockett's fascinating papers several years ago, that was on minimum attention control. Roger Brockett was looking at this functional of the control, that is a function of the state and time, and the derivatives of the control with respect to state, and the derivatives of the control with respect to time. And he calls the derivative of the control with respect to time, or a norm of this operator, a measure of the feed-forward action, and the derivative of the control with respect to state in a norm as a measure of the feedback. And of course, you see that the dependence on state is feedback, and the dependence of time is basically the variations that you have pre-programmed. Brockett was putting attention on the fact that people, when start learning skills, physical skills, at the beginning use a lot of feedback. Think of a piano player. That was exactly the example that Roger used to give. When you learn to play piano, you look at your fingers and you pay attention to your feedback, tactile feedback, a lot, and you execute mostly in feedback. But while you learn, you go more and more in feed-forward, and you release the attention to feedback. So it calls this attention functional, and it is interesting to see that by the iterative learning control that I just discussed in the slide before, you see that during iterations here, the error decreases in the three cases here, 1, 2, or 3 degrees of freedom that you see on this scale. While if you look at the ratio between the feed-forward control and the feedback control, you see that it goes increasing. While you learn, feed forward increases and feedback decreases, just like you would expect from something that is inspired to what humans do. There are a few more experiments that I want to go quickly through. Here is a robot that has learned the operations that we just showed before through ILC, and now it's executing with different stiffness that we do not know. It turns out that if you do position ILC, that means you learn how to position the joints with one stiffness, and then you execute when the robot has a different stiffness, then the execution is very poor, as you can see, for instance, here. But if you learn the right thing, which is you learn the torque that is needed to apply the current motion, then you can see in these animations that the robot executes the trajectory correctly, whatever stiffness it is presented with. So it learns with, let's say, soft, and then it executes with stiff, and still the correct motion is achieved. And here is a comparison. The results are mainly due to Riccardo Mengacci. So what messages can we take home? How can variable physical impedance of SAW robots be exploited usefully? Database control tools use experimental data to build an empirical model of the system. It has high robustness until the system is changed. There is little insight that you get, unfortunately. And the open problems are that many data are needed. That implies long learning time. You have to try many times to do something, like tens of times to do something before you can execute rather accurately. And of course, this implies that the robot wears, parts break, and so on. Also, the problem is, how do we generalize what has been learned to new cases? If I learn to do a number of operations, can I interpolate the lessons that I learned to do something that I never tried before? Of course, to increase the robustness of database approaches to robot environment changes, then you can think of merging model-based and data-based approaches. Another interesting evolution that we are now trying to use is the so-called sim to real, which is using simulation to learn real control. Articulated soft robots are partly there exist already some simulators for series elastic actuators, as some of those are in Gazebo and ROS, which are C++ libraries of kinematics and dynamics for SCIA. But if you have variable stiffness, there is none that we know. So recent work by Riccardo Mengacci and Grazia Zambella has created a new tool in Gazebo for doing realistic simulations of variable stiffness, variable impedance robots. And you see here that the simulation is rather close to reality. So if you can develop very good simulations, then you can think of teaching a simulation, and you can do that for as long as you want in background on computers that can be very, very fast, and then apply the learned lessons to the real robot. And you can see here that this is a very recent experiment that Riccardo and Grazia did. You can see here that these are the errors achieved during learning on the simulation. And when convergence was reached by the simulations, which are the blue lines here, within the tolerance to the desired dashed curve, then the control was applied only once to the real robot. And the real robot already very soon behaved in the correct way with respect to the specification. So it is possible to learn, but of course, we had a very good model of the reality here, and that is not the case always. So coming towards the conclusion, I want to touch on learning more complex tasks that are around. So we need to learn not just moving, but doing more things. And we want to have robots that can be used not just by programmers, not just by insiders, but by general public, the common people. So how can we do that? Of course, learning takes a long time, as you remember from the experiments in grasping from Google. Uh, there are other approaches, which are, for instance, learning from demonstration. Uh, and there is some work that Gianluca Lentini is doing recently that tries to learn just like kids do by showing them once, at most twice, a task and try to repeat it. So here is a setup. Gianluca is here wearing very simple interfaces to control the two-arm robot with a head. The head copies the motion of Gianluca's head, and the arm copy Gianluca's arms. We also have EMGs to measure the muscle contraction at the arms. Here is Gianluca, and here is the operation. So first thing is you teach the robot to take this tape and put it in the final position on the green bar. If you do it once, you shouldn't demonstrate that again. Of course, the robot can pick, even if the initial position is not the same, the robot should be smart enough as to do that again. And there is actually little that you need to do in order to make the robot understand that two tapes still go on the same bar, even though the bar is not longer where it used to be. Of course, if you have new objects, then you have to teach the robot where the new objects go. And this can be done very simply. And then executed again by the robot. I will not go too much into the details of how the method works, but it's a very basic learning by demonstration algorithm with some variations that I will mention later on. Of course, once you have learned an operation, you can repeat it, even at twice the speed, as you see on the right, whatever is the initial position or final position of the goals. Now, today's topic is to have interaction. So think of teaching the robot by the same method to put this peg into the hole. You can use a stiff robot, and then the person is now looking at the robot and inserting the peg in the hole. He can do that because he is a human and he knows how to do it. So it has a successful demonstration. But when you repeat it autonomously, the stiff robot is not able to do it again, basically because the interaction forces are too high and it gets stuck. You can then try to do the same task with a soft robot. Again, the human can do a successful demonstration of the peg in hole because he knows how to compensate for the deformations introduced by softness. But when you go to execute it again, then the robot fails. In this case, because it does not have enough force or enough stiffness, rather, to insert the peg in the hole. So you have a final error in force and a final error in position here. What can we do? Can we have a variable impedance, and can we also teach the variable impedance? So the idea is that you have a robot and you have the person. We can measure the impedance of the person, both by looking at his configurations and by looking at his co-contraction level, the contraction level of his muscles, activation level of these muscles, and or her muscles. And then you can work on the scheme that basically is a alignment of the perceptual cues that you have along the execution by the human. When you demonstrate not just the postures, but also the impedance. And the saliency point during the operation tell you when it's the time to change a given posture or to use a given impedance. So if you apply this, then the person can change the impedance. The impedance is measured during the demonstration, and the demonstration is successful. But also now, during the autonomous execution, the robot uses the right profile of impedance in the different phases of the operation. And you see here that not only the forces and positions are now matched, but also the stiffness of the person is matched during the task. So with this, I close my talk. I've been a bit long. Human impedance is variable both during and among different tasks. Part of this variability is intentional. Impedance variations are controlled by muscle and co-activation and arm posture. The robot impedance can be varied by both software and hardware means, and it can be controlled varying gains and arm posture. Planning can be done in different ways. We can use insight from optimization. Humans can control variable impedance of robot through tele-impedance, which is what I just demonstrated, measuring the human impedance and replicating on the robot. And recent work shows that robots can learn impedance behavior from few human examples. There are many open questions that are left. Of course, variable impedance control comes at a cost. If you have hardware, then basically you have twice the number of actuators if you want to have variable stiffness. If it is in software still, you need force sensors, you need better hardware or open architectures. Very few industrial robots today have programmable impedance. It comes to a cost, so it makes you ask the question, is it really worthwhile? When it is worthwhile? And I think that this question is not completely solved yet. There are many like us who believe that there are cases where it is worthwhile. Humans do use variable impedance, but is it there on purpose or by accident? Do we have variable impedance because we have it, and we have it because our musculoskeletal system is just happens to be built the way it is built, or rather it is there because of a causal reason, and we can do what we can do because we are built this way. A final important question is that it would help us to answer this question if we knew exactly how humans use impedance. To do so, we would have to measure impedance. But unfortunately, measuring impedance in humans is not easy. The only method that we have use perturbations. There are no methods I know of that can measure impedance without perturbing motion, and to do that in real time. With this, I would like to close the presentation. I'll be very happy to listen to your question. I want to thank the BRIG group. I mentioned a few of the co-authors of this work. I'm really indebted to these people and the others that you don't see in this picture. There are too many to make the names, but they have been quite an adventure to work with and a blessing. Thank you very much.
Thank you very much, Antonio, for a very insightful and instructive overview on the topic of variable impedance. In particular, I really liked how you drew connections between humans and robotic applications. So today, we are pleased to have a very distinguished guest panelist, Professor Neville Hogan, who is a professor of mechanical engineering at MIT. As it is the tradition for this robotics seminar, our guest panelists will go first with the questions, And then we have other questions from the other panelists, namely myself and Alberto, as well as from the students. And please submit your questions through Slido if you want us to relay your questions to the speaker. With that said, I will turn the stage to Professor Hogan.
Thank you. And let me first say, Antonio, that was a spectacular talk. You have taken this a very long way, so I'm really impressed. I want to start with a kind of vague philosophical question, but so I'm convinced that, you know, variable mechanical impedance is an important part of how humans do what they do. How much might it also be related to human perception? So, you know, so we also, you know, we perceive what to do with objects. We perceive things like we can guess at the effective stiffness of some other entity or person. Do you think that the same framework could be used to describe cognitive and perceptual performance as well as manipulation and motor performance? Any thoughts?
Not sure I can understand the full depth of the question. So your question is not the relation between the mechanical impedance and perception, or is it, or does it have to do with the impedance of perception? Can you explain it a bit better?
So what I'm getting at is that we know from a lot of prior work that humans can extract an enormous amount of information from very sparse data. So there's these displays of point lights that move, and people can detect the gender of the mover and so on. So, you know, we're able to pull out an enormous amount, and that's based on motion. Do you think we could be able to do similar things, figuring out the impedance? So, for example, if I watch, say, a skilled craftsman using a tool, I might get some sense of the fact that, well, he's actually increasing impedance here or decreasing it there.
Okay, yeah.
Okay,
That is a very good question. Yes, I completely agree. We can tell that, right? I mean, as humans, we can tell that. We can see whether a person playing piano is a novice or is an expert, or someone doing any other task. So by the fact that is, you know, you're stiff, you're uneasy, and you see that from motion, just by looking at the motion. And I'm not now, I wouldn't be able to cite a paper, but I would bet that there must be work that shows from motion capture data that you can infer some information on the impedance. Although, as you know very well, measuring impedance in a more precise way, as I mentioned lately, is not easy. Basically, because impedance is a relation between the torque or force that you measure and the displacement. And displacement is defined between where you are and where you would be. And no one is to tell us where you would be in your body, because it's basically your brain that tells where you would be. But no, we cannot talk to your brain, nor even to ours. So that makes the question very difficult. I agree that, of course, there are ways. You are interested in this problem, I know well. Perot is interested in this problem. There are many people working on this, and I trust that this will be at some point understood. And the observations that you were mentioning are definitely at the core of these techniques. So let's hope that we can do that to understand better.
Other questions from Neville?
I can continue, but if there are questions from the audience, it's probably more appropriate.
Okay, so I'm going to just ask a question about one of the very final points you made. And I was wondering if you could elaborate a little bit more on whether variable impedance is worthwhile. and whether we need new advances in either hardware, software, or maybe application domains to make it worthwhile at a broader scale.
Yes, I think it's something that we debate often. I mean, people like us working on variable impedance have this question posed. Now we see now that more and more robots in the commercial framework have the possibility of doing impedance control, and that is definitely encouraging, because it means that there are tasks, and the classical assembly tasks, for instance, are important tasks where you want to have that. So I think that then the question whether it is software or hardware is not really dominating, is not really important. Whatever gets it done is probably good enough. As I said before, commercial arms that implement variable impedance typically use force sensors at the joints, so still have some hardware modifications in them and some more cost. Variable stiffness actuators, so far, they're very, very young. I think they are a little more than 10 years. So they will come, perhaps. Definitely, we can also hope that we will have new actuators that are not electromechanical out of all the work that the community is doing on soft robotics, continuums of robotics, and new materials and new principle for actuation. We definitely hope that some practical actuator will come that we can use even without, use, not do research on. So I think it's still a long way to go. There is a lot of research to be done. In my talk, I tried to make it to make the point that it's not only about building VSA, it's also about controlling them, because they really change the paradigm. But I do think that it's useful and important.
Okay, thank you. And we do have some questions from the audience. Maybe Abby, you can ask one.
Sure. Thanks for the talk. So this is one of the audience questions. It's a somewhat open-ended question of the idea behind soft robots. They often take inspiration from nature, where the performance of the organism itself varies over its lifetime. So have you thought about how that reflects in the hardware, and whether that also trickles further up into maybe the controller design or the modeling of the systems in terms of lifelong behavior?
Sorry, what is that? So we get from the nature, but
yeah, so in nature, the performance of the organism itself kind of varies over its lifetime in terms of its material properties and such. And has that kind of influenced how you've designed systems or even designed the controllers for particular robots?
Yeah, yeah, being nature inspired is a mixed blessing, you mean? you get older faster, perhaps, or yeah, that's the luxury of robotics. You can take inspiration, but you keep your degrees of freedom not to exactly copy or mimic nature. Yeah. I mean, speaking of materials, there are many things that you can try to get from nature. For instance, those self-healing robots that can fix themselves, for instance, the work that several people are doing, including Bram van der Boort, for instance, with a very nice project, and the other materials that can show excellent properties in terms of density of power, for instance, better than many electromechanical. It is true that if you look at the numbers, the sheer numbers, electromechanical actuators are not that bad. If you compare with human muscles, the density of power and is not worse, actually, but per mass. Nonetheless, there are things in the natural example that are still outperforming us. So I think in some sense it's itself is a matter of wonder and deserves investigation. How it comes that we have, nominally better motors already than we have muscles, which in numbers are not so excellent, but they work so much better. So we have to probably better understand the metrics.
Yeah. Maybe as a quick follow-up to that, I can ask, going the other direction as well. So equipping, say, more mobile robot platforms with, developments from like soft robotics. So I guess I'm thinking of, say, like a quadruped platform that's capable of doing like footstep placement on like uneven terrain. Like, have you thought of those kind of like other applications in robotics where these might be useful?
Well, we use a lot of this. I didn't mention today, but we use a lot of these ideas for doing hands and more recently feet for robots. And those soft hands and soft foot are devices that we believe are helping a lot in doing more stuff and more interesting stuff with robots, because they have this inherent adaptability that ends up to be intelligence, in embodied intelligence, if you want. So the soft hands or soft feet can adapt to the environment and give you better performance, definitely. So those apply to many applications, many different fields. And that is a line where we are seeing concrete results. If you apply those ideas from robotics to prosthetics, for instance, turns out to be very fruitful, because the simplification that comes from the embodiment of intelligence in the device itself, in the physics of the device itself, makes the controller easier. Now, today, in a sense, reducing the complexity of the programming doesn't seem to be such a important thing to do for robots, because we have all the power of GUI and all the Google compute. You don't seem to want to spare on some lines of code. But if you do prosthetics, then it's a person who has to control the device, the hand, for instance. And you cannot ask the person to be absorbed cognitively in the control of the hand or the foot. So people need to use their hands without thinking. We do that every moment in our life. And therefore, there you can really appreciate how much the simplification that comes from embodying intelligence in the low level, in the mechanics and the firmware, basically, of the devices is important to solve things better.
Thank you.
Thank you. And I think Alberto has a question.
Yes. Hi, Antonio. I'm glad to hear that you brought up the hand right at the end of your answer, because it connects to what I wanted to ask you. In many of your videos, the arm that you described today is connected to a hand that also happens to be soft. And I wanted to ask you if you can give us some details as to whether it is soft in the same way as the arm or in a different way, and the relationship between those two. Okay.
So the hand that we used, and I didn't mention today because I give too many talks on the hand, and I thought that this was the time to change subject for once, is soft in the sense that it is articulated soft. It has deformable elastic connections, and it can deform, even displace the joints. But the mechanism that is behind the actual working of the hand is rather adaptive than properly soft. So it's not just elasticity, but it's a way of mimicking elasticity, if you want, through a differential a complex differential gearing. And so it is soft in the sense that it adapts to the environment. It moves according to a predefined pattern, a primitive that is observed in humans at rest. But then when it grasps an object, its shape is defined by the interaction, by the elastic interaction with the environment, with the object itself. So it is attracted towards this reference synergy, we call it, but it is repelled by the object, and in the end, it reaches an equilibrium. So the net effect is exactly that of a soft hand. The way it is realized is not exactly, is not only through soft materials, but is rather through this combination of mechanical design and firmware that is this embodied intelligence in the low level.
So let me follow up. Like, I hope it's okay to point out, like, in the explanation of the softness of the hand, you didn't mention the word impedance.
Yeah. Okay.
Or variable impedance. Like, why is that?
Yeah. Okay. So if you have the hand that grasps an object, and if you apply a strong force on the tendon, then the hand gets rigid because all the adaptivity has been absorbed by the shaping of the hand. So in that sense, in that configuration, when you have high force, the hand is no longer soft. And that is on purpose, because when you want to interact with the environment and a prosthetic hand or a robot hand has to, has to lift 20 or more kilograms. So you don't want to have something that just gives, that complies too much. So you want it to be stiffening up, like all our muscles. They're non-linearly soft. Right? They get stiffer the larger the load you have, the stiffer they are. If you want to change the impedance of the hand, you can do that, but by changing the gain of the controller of the motor. So you can have the hand that behaves softly or more stiffly. If you change basically it's an impedance control, the simplest form of impedance control. You change the gain between position and between displacement and force and torque. So if you do this, you achieve de facto a impedance control. And I didn't mention this because it was not in the main line of the talk. But it is interesting that you ask, because then I can elaborate a little bit on the usage of this. And again, the most evident usefulness of this variable stiffness of the hand is that our subjects, the people that use the hand as a prosthesis, and there are many now, they appreciate the possibility of changing the stiffness for interacting with different objects. For instance, when you interact with something that you have to do in a precise way, they use a stiffer configuration. When they interact with their own body or with some other's body, like shaking hands, then of course having more compliance is appreciated. And we have done experiments also in the perception that others have of the hand when they shake the hand with the person that uses the hand as a prosthesis. And the social perception of the robot hand is much improved in the case that it is controlled with low impedance, which adds a new dimension, if you want, to the talk. So another utility of the variable impedance approach is that it makes robots more likable by people who interact with them.
Okay. Thanks. We have actually another question from the audience. Rachel, can you chime in?
Yeah, this is an anonymous audience question that I think is about representation. they ask, where do humans store muscle impedance parameters, and how do they recall those parameters when manipulating known objects? I think it's for you to speculate on.
I I think Neville knows a bit more than I do on this. I know very little where we store information. Let's say, I don't think the question is exactly which neuron stores it. I think the question is interesting though, in the sense of how we represent impedance in our, and frankly, I think it's a very interesting question, because I never met with literature studying where we have this image of impedance. I think, for instance, I was referring before to synergies, and we have seen that synergies have a map in the cortex. I mean, this organization of our hands does map to the cortex. So it is possible that this impedance mapping is in the cortex, but I'm not the person. I mean, I'm not really the person to hold the literature. But as far as I know, I don't remember any paper discussing that. It is important the way we represent impedance in our brain, because then it would also give us a way of doing this. In our little experiment that I showed before, the robot learned to associate different impedance patterns to different situations along the execution by looking at the position relative to the environment. But that was, I think, kind of, you learn that when you are far away from any part of the environment, you might be stiff. When you get closer, you want to be stiff in the directions where you have forces, and you want to be, you want to be soft in the direction where you have higher forces, and stiff in the directions where you don't. But that is not probably what the brain uses.
All right, I think it's time to wrap up. Alberto, we would like to make.
Yeah, thank you. I guess just thanking Antonio again for being here with us today. It's been great to learn about variable impedance, the fundamentals of variable impedance actuators, as well as control mechanisms, both in humans and in robots. This is the last talk of the semester, where we've had a very broad set of topics, ending with Antonio, including Kaushal Srinath, who talked to us about controlling hybrid and dynamic robots, Amanda Prorok, communication in multi-agent systems, Raya Hatchell with the scalable robot learning, Chad Jenkins in AI mistakes and Black Lives, and starting with Adam Bry and Heike Martinez from Skydio on autonomy in visual navigation and 3D reconstruction with drones. It's been an honor to be here again this semester, and thanks especially to the audience that you've been there, and have a nice summer.